All right, in the second video, we're going to be working through the process of producing both a point density and a kernel density surface. The most important thing I want you to understand is that before we do anything else, we need to make sure that our point observations are in projected units, because again, we're going to be doing cell sizes that are regular. That is, they have to be in planar or linear units as opposed to degrees. The other thing I want you to think about is what your output is going to look like and really what it represents. If you'll notice in the point density, what we are doing is producing a radius, a search radius around each observed point. In contrast, what we're doing in a kernel density is for each grid cell, we are producing an area of influence to that grid cell in terms of the count. And so what you'll notice is that in point densities, we tend to get these regular circles of influence, and that really is the count within that search radius. Whereas in the kernel density for each grid cell, we're looking at, from that grid cell out, the number of occurrences of our phenomena and how far they are from the grid cell. So again, if you think about it, you're going to get two very different looking surfaces. One is very much going to have our circles of analysis, while the other one is going to have, in a sense, hills and valleys of density. So again, different ways of understanding it. It's not that one or the other is right, it's that they tell us different things. One, point density, looks at each point and its neighbors, whereas kernel density looks at each cell and the number of phenomena and their proximity to that cell. All right, so again, important to understand that distinction and how the idea of the search radius from that sample point is represented in that grid cell. So again, if we think about it, what we're saying here is for this grid cell, each of these surfaces, each of these radii from, here's our a phenomena, here's a phenomena, here's a phenomena, here's a phenomena. The value for this cell is the result of each of these overlaying that cell and how far we are away from the center, if you will, of that kernel. So again, it's important to understand that distinction. All right, so here's what we're going to do. We're going to go through some basic steps, and I'm going to outline them here, and then we're going to look at them, in fact, in ArcPro, and you are going to produce two raster surfaces, and then we're going to calculate their difference. So step one, very important. We're going to take our Bigfoot observations, and we're going to change their coordinate system. Okay, right? I shouldn't say we're going to change it. We're going to project that data so that it is an Albers equal area US GIS. Then we're going to do two different point analyses. The first, we're going to do a point density surface, and we're going to set the parameters, and I'll show you those in a moment. And then we're going to do the same set of parameters, but we're going to use a kernel density. And then finally, we're going to use map algebra to calculate how these two differ. Okay, so let's get started. All right, before I go any further, though, I want to just show you what your parameters are going to be, and then I'm going to open up ArcPro and we'll go through it. When we do a point density, the main ideas that we're going to want is you're going to produce an output that is going to be point density, and we're going to use a 10-kilometer grid cell size. It's going to calculate it fairly quickly that way. So our input is going to be our projected Bigfoot points. Our output is going to be a point density at 10K. Our output cell size, we are going to set at 10,000. And so again, since we're using meters, this is going to be 10,000 meters or 10 kilometers square. Our neighborhood, our circle of, if you will, of analysis is going to be 100,000, okay, 100-kilometer search distance. But we're also going to then set our environments. And in our environments, we're going to set our output coordinate system to be our Albers equal area, and we're going to use the USGS version. We're going to set our cell size to the maximum of inputs. We're going to do this one first. And we're going to run our tool. All right, so let's get into this and take a look at it. Okay, so we are in ArcPro now, and you'll notice we've already done our vector-based density analysis, and we have our Bigfoot observations here. And again, I have some other things in here that I've already run, But what I want you to do is notice this, that the first thing I want you to think about is our Bigfoot observations. If I look at their properties, the source says their spatial reference is geographic, and we don't want that because, again, we have angular units and no planar units. So we need to change that. And again, the way that we do that is we make sure our map, the easiest way to do it anyway, is to go into our map and set our map properties. Now mine have already been set, but I'm going to go into my map properties, and for all of you, map properties, we're going to go down to our projected coordinate system. Okay, so projected coordinates in our map. Again, notice that I'm in a map here. And I'm going to go down to the continental, and I'm going to expand that to North America. So continental within our projected North America. And then I'm going to scroll down until I see the Albers. Scroll down to this one right here, and it's going to say Albers contiguous USA, or USA contiguous Albers equal area conic. And again, contiguous means just the continental United States, and we're going to do equal area because we're doing an area analysis, and we're going to use the US GIS version. I'm going to click OK on that. Now that's set, and again, mine was already set that way. Looks like this. Now the other thing you'll notice down here that my units are in meters. Yours may or may not be in that, because that is part, if I go to properties again, what I can do in terms of my general is my display units and my map units, I want to be meters. Okay, so again, you can check those here, but we want to make sure that your display units are meters as well. I could display it any way I want, but you'll notice that I can't change the map units here. The map unit, the true map units are this. We can display whatever we want. We can convert whatever we want. But we need that first. Now, the next thing that I want you to do is right-click on your Bigfoot observations, and we are going to export these features. Again, this is a way of projecting our data. So I'm going to click on Export Our Features, my Bigfoot observations, and then what I want you to put down are, I want you to change its name to Bigfoot Albers equal area. That way you know that this is what you're getting, is an Albers equal area projection. Now, environments is the next piece. We're going to click on environments, and we're going to say our output coordinate system is the same as the current map, and you'll notice that it says now Albers equal area conic. We're going to click Run. And you'll notice that now I've projected my data, and I can close that. And from now on, I'm going to turn off these. In fact, I'm going to remove them from my map so I don't mess this up. And I'm always going to work with these projected points. Now you'll notice they look the same. All right, so that's step one. Always project your point data. Now, the next thing we're going to do is we're going to go into our tools, and we're going to select point density. Now again, if mine kind of comes to that, if you click on toolboxes, go down to spatial analyst, density, and we're going to click on point density. Our input point features are going to be our Albers equal area Bigfoot data. We don't have a population set, but what we're going to do now is put our output raster. We're going to set to, and let's call this one point, well, I'll just put point, PT, density, and we're going to use our cell size, 10K. So PT density 10K. That's what I want you to output. Now our output cell size is going to be 10,000. We're going to use our neighborhood that's a circle, and we're going to go out 100,000 from the center. Okay? Our area units are going to be square kilometers. Now the next thing we need to do is change our environments. Click on environments, and we're going to set our output coordinate system to the same as the current map. We're going to leave all of these alone, and for you, you can leave this maximum of inputs, but I do want you to change the mask, and hopefully you have the state boundaries on your map. If not, you need to add it, and we're going to use the state boundary as our analysis mask. Now, once that's done, you can click Run. So again, just going through these, state boundary is going to be your analysis mask. You're going to put Albers equal area, and that is the same as the current map. We're going to put 10,000 and 100,000. All right, so now we're going to click Run. Now, one of the things that happens here, I just want to be clear, is that the display option here, so now what we've got is population density, 10,000 meters, 10K area, and these are in, our value is actually observations per square kilometer. It's important that you understand what your units are. The other thing that I'm going to do is I'm going to change its symbology. And again, you can do this or not, but you'll notice this kind of checkerboard here. That means that that's transparent, and I really don't want that. I want to see where the zero values are. So I'm going to take a single color in my case. I'm going to use this one. And now you can kind of see what's going on there. And you'll notice that I have higher concentrations here. I'm actually going to turn off my points so that we cannot see. If I can scroll up here. And you'll see that kind of pattern there. Now you'll notice that it looks somewhat similar to a kernel density, but we have a very high one here and some highs here. Now, before we get any further, we're going to do this again. And again, we're going to be using our Bigfoot, but in this case, we're going to go into our tools and we're going to do a kernel density. In this case, we're going to, again, use our Albers equal area big feet. Our output is going to be our kernel. Okay, we just used point density, so we're going to use kernel. And again, we're going to do 10K. We're going to put in the same output cell size, 10,000. And our search radius, we're going to put in the same, 100. Oops, put in too many there, 100,000. Planar method. Again, now we're going to go into our environments. Again, same as the map. The cell size, what we're actually going to do is we're going to use our point density. I'm going to click on that one so that they will match each other. And then we're going to use as our analysis mask the same thing, state boundary. Now, once we've got all those set, again, these are here. We're going to go into our parameters. Remember, 10,000 and 100,000. And we're going to click Run. And now, again, I'm going to do the same thing. I'm going to go in here and look at my symbology. And rather than have this, I'm going to use a similar color scheme here. I'm going to make it a little different, though. I'm going to pick, let's do a single. Again, remember, since we have one value, we're only going to use a single color scheme here. And again, I'm going to turn off this. And what you'll notice is that if I kind of toggle back and forth between these, they're similar, but they're not quite the same. And again, if we look at our values here, these are these are per square kilometer. Okay, and that's a kind of the global average, if you will, across our total data set. So this is observations per square kilometer. And then the same is down here. Observations per square kilometer. And so we can see that these are in fact different. But the question is, how different are they? So the last thing that we're going to do is we're going to compare the two. And so what I want to know is the difference. And that's really quite simple to do. We're going to click on our tools. And in this case, we're going to go again into our spatial analyst. But instead of going in again, remember, you click just on toolboxes, go down to spatial analyst, and we're going to go to our map algebra and our raster calculator. And quite simply, I want to know the difference between kernel density minus my point density. And I'm just going to call this my point. We'll go here. PT kernel difference. PT kernel difference. I'm going to just click Run. Now, what you notice here, let me get rid of that. I clicked the wrong place. And again, I want to leave this open. So again, what we have is kernel density minus point density, and we have an output that is the difference. It's important to understand what we've just got. And so I'm going to kind of minimize these two. And let's see what we have here. Well, what we have is a difference that runs between 2 100ths per square kilometer to a negative 1 100th roughly per square kilometer. Now again, this is probably hard to see with this color scheme, so what I'm going to do again is go to my symbology, and because I have both positives and negatives, what I want to do here is choose one that goes in both directions. And now what I want to do here is I'm going to say display my background values of 0 as no color. And what you'll notice is that now if I were to turn the other things off, that in fact this is where I have either positive or negative differences, and out here that's where both of them calculated zeros and they weren't any different. And so it's a way of analyzing where we have significant differences between the two models. Now, what I want you to turn in for this part is different screen captures. Again, go through your screen captures, and the first one I want is the point density. The next one I want is your kernel density. And then lastly, just a screen capture showing the point kernel difference. Okay, that's it for point densities. We'll pick this up in the next video on analyzing those patterns.